Okay, perfect. And so the next speaker is Victoria Sevostyanova from University of Samara, and she will talk about invariants of equivalence classes of the set of tight frames. Please.
Okay, thanks. Let's start. We will talk about frames in a finite-dimensional Hilbert space. The base field is a real or complex field. Let's start with the definition. What about a frame? A frame is a complete family of n vectors from a d-dimensional Hilbert space. It's in some sense frame generalized concept of a basis. Of course, there is no linear independence requirement for vectors in the definitions, but this construction can be useful in many cases, and I'm sorry. Okay, the family of vectors is called a frame for a space if there are such numbers A and B that these double inequalities is these numbers A and B is called frame bounds. We consider the case when A and B are equal. So the next definition is the definition of a tight frame when the bounds are equal, as I said. We consider normalized tight frames or Parseval frames when these parameters are equal to 1. As usual, if we fix the standard basis, we can write frame as a matrix such that the columns of this matrix are vectors of a frame. So, what about example of tight frames? That's not difficult to construct such frame. That's sufficiently to take some unitary matrix and delete n minus d rows of this matrix. So the result, columns of the result, make a Parseval frame. There are two operators for frame synthesis analysis. The first operator works like that. If we decided to construct a transformation of a vector y or vector x to in a d-dimensional space, we should multiply frame phi on x on the column x. And so we have the definition of analysis operator. Okay. So we can construct two operators, a gram matrix operator and a frame operator. Here it is. The first equivalence that we will need is a unitary equivalent. We will say that two Parseval frames are unitarily equivalent if there is a unitary transformation that that make one frame to the other frame. So everybody knows the result that Parseval frames have the same gram matrix if and only if these frames are unitary equivalent. That's very simple result. Okay, let's talk about equal norm tight frames. More interesting case. A frame is a tight if frame operator is a diagonal matrix, then we have that any vector can be reconstructed from the frame by this equation. That's very simple reconstruction. So we will say that phi is an equal norm tight frame if this frame is an equal norm. Exactly. For an equal norm tight frame, we have the equalities. What about examples? What about examples? The construction of equal norm tight frames in a complex case uses the matrix of the discrete Fourier transformation, and the first construction of such frames appears only at the beginning of our century. What about equal norm tight frames in a real case? That's not simple to construct such frames, and there are very small examples of the frames of the following case. The first example of such frame was constructed by Maltsev in 1947. This paper was published as an answer for a question by constructing a matrix with orthogonal rows of unit length and columns of equal length. In fact, it was the first construction of equal norm Parseval frame. So let's continue. The other interesting examples of frames are equiangular frame. If frame are equal norm and scalar products have the same norms in frame, we will say about equiangular frames. The main problem when we would like to find some example of such frames is due to the fact that the starting point for constructing equiangular tight frames is the existence of equiangular lines inside. Equiangular lines in space. I mean a vector and a minus vector are the same up to some equivalence. We will call this equivalence projectivity equivalence. So equiangular tight frames are very necessary in some sense because they used in some theory and used some specialists in signal processing, communications, coding theory, quantum theory, and these frames appeared in discrete geometry, but today have many applications. What about examples? The simplest example is the case when the number of vectors is equal the dimension plus 1. So we can show that there is a unique equiangular Parseval tight frame up to some equivalence. Projectively equivalence means that a vector and minus vector are the same. Unitarily equivalence we discussed before. What about equivalence to reordering? It means that vectors of the frame consider it up to a range in the set of the vector frames. So the other result that was proved by Sergei Novikov and that's my result, that in the case with 5 vectors in the 10 vectors in the 5-dimensional real space, there is a unique vector. Look at this matrix with 10 columns. 10 columns are in a 6-dimensional space, but really they are in a 5-dimensional. You can see that these columns are make equal norm equiangular prime. That's. So we have the same result for the case when d equals 3 and n equals 6, and for the third case when d 7 and n 14. Okay. Here it is. You can see the definition of projectively unitary equivalent frames. So these two examples shows that there are not projectively unitary equivalent frames, that unitary equivalence is not sufficient. So more special dividing frames. Okay, everybody can check grammatics and see. Okay. Consider the other unitary equivalence up to reordering. We will say that two frames are unitary equivalent up to reordering if there is a permutation that rearrange the vectors of the frame. So you can see two examples. Columns of these two frames make different gram matrix. Let's talk about unitary equivalence. Let's come back again. From this point, we will say that the general field is real field. The theory can be constructed for the complex case too, but that's not difficult. But now we will talk about real case. This theorem shows how we can reconstruct a Parseval frame from its gram matrix. That's an orthogonal projection of a gram matrix, so that's a simple way. It means that if we have a gram matrix, then we have some Parseval frame. Okay, let's consider the real Lie group of unitary equivalence with the d rows and d columns. Any element of this group acts on Parseval frames by left multiplication. So we have the other frame like that. And we can see that this action leave a Parseval frame, leave a frame Parseval. Yeah. One can see that this action on Parseval frames is transitive. The other case, the other point is that that unitary equivalence classes are the orbits of this action. So, because the action of the real I'm sorry. Unitary. I'm sorry. Yeah. Because the action of the real unitary group on the set of Parseval frames is transitive, then the set of Parseval frames is a reducible smooth algebraic variety. So we can continue this action on the gram matrices of Parseval frames and get that this action on the set of Gram matrices will be transitive too. So the set of Gram matrices of Parseval frames is a smooth algebraic variety too. So consider the action. One can see that this action is surjective and is invariant under the action of the unitarily group. Yeah. So we have the theorem that the field of invariance is generated by scalar products. Right. That's a simple result. And we will continue this result on the equivalence up to reordering. Consider the symmetric group and consider the action of this symmetric group on Gram matrices. Evidently that we should consider the action not on Gram matrices, but on symmetric matrices. So consider the formal matrix with variables, and let M be the set of real symmetric matrices. So we can continue this action on the ring of polynomials and on the field of rational function. Now you can see the set of invariants under the action of a symmetric group on symmetric matrices. So the first series S, this is a symmetric polynomial of the diagonal elements. So that's evident that these polynomials will be invariant. But the second series T is not evident that that's invariant. Okay, we have the map that calculates these polynomials for any symmetric matrix. Okay, we prove the theorem that there is an open neighborhood in the set of symmetric matrices such that this map is an epimorphism in some sense. Yeah. Oh. So we have that the field of invariance of the action of symmetric matrices of the action of symmetric group on symmetric matrices is a free field of polynomials S and T. So besides, we have that these polynomials are algebraically independent. Now we can continue the result to the case of Parseval frames. So if we replace the set of symmetric matrices by the set of Gram matrices of Parseval frames, we have the theorem, the first theorem of the frame. The second result is that field of invariance for unitary equivalence classes up to permutation for Parseval frames is generated by these polynomials when variables are scalar products. So literature, and I'd like to point out the number 4 and remember Frame Research Center by Casaza. He is the head of the center, where you can find more interesting information about frames. So it seems that I finished. Thanks.
Okay, thanks a lot for your talk. Are any questions? So comments, observations. Okay. Doesn't seem to be the case. Okay, then thanks once again for your talk.